Okay, physics. So let me see if I can show you algebraically why it is that you want to aim the banana directly at the monkey to make sure they can catch it. And again, it's a way of using algebra, so I hope you get out of this. You don't need to know how to derive this, but I hope you get examples of interpreting the algebra as we go along, because there's some interesting consequences that turn out to be help you understand why this is the case. So here's the challenge, right? So I have a zookeeper is going to shoot shoot a banana towards a monkey, right? So originally this had a different thing. They were shooting at the monkey for a different purpose, but yeah. So here's my monkey hanging, and what hopefully you've seen already or you've been told is that to hit the monkey, I have to aim it directly at the monkey, and if I fire the same time the monkey drops, that then this will take a parabolic path and it will meet here. The monkey will be able to catch the banana. So something's going to drop. So it's kind of not necessarily intuitive, but we can get there with algebra to show this. So so that's the purpose of this video, to show you how the algebra can get you there. So let's think. So we're going to have two things happening at the same time, and my projectile I'm going to break into x and y components because it's at an angle. I'm always going to do that. So really I'm going to have three things I'm going to keep track of. So first thing, so I have my projectile, my banana, some angle. So this leg, my horizontal, so let me say my horizontal projectile. What do I know about it? Well, it's going to have this leg of velocity. I'll call this initial velocity v that it has. So the velocity of this thing is going to be the cosine. So it's going to be, v of my x is going to be the original velocity times the cosine of that angle. Okay. The second thing, what do we know about this? So it's going to travel some distance to get there, right? So that horizontal distance is going to travel between here and here, right? So I'm going to call this distance, I'm going to call this d. So it's going to travel some distance d. So the distance it travels, I'm going to call that d, and the time it takes, I'm going to call that t. Right? Okay. So yeah, so that's pretty good. So that describes the horizontal motion of this. So let's think about the vertical motion. So what's happening to the vertical motion? Well, where am I starting? Well, I'm going to say my vertical position I'm starting at is going to be 0. I'm going to make this my base, right? So notice what I'm doing. So I'm calling this positive, and that makes downwards negative. So if I make this positive, this is 0, everything above is going to be positive. So where's it going to end? Well, I'm not sure. So let's come up with some names here. I'm going to say, well, where he catches it, I'm going to call this the height h. Okay, so it's going to end, the end position is not going to be back at 0. Well, it could be if it falls all the way down, but I'm not sure where it's going to be. It's going to be some height. What else do I know? So I know the initial velocity that I start with, vy that I start with, is going to be this component of my triangle. So this is the opposite leg. So this is going to be my original velocity times the sine of the angle. What else? I don't know my final velocity, and I don't think I want to figure it out. I know acceleration. This is going to be negative g. And there's going to take some time, right? So time is going to be a good connector for this. So time is going to be the same across these. So that's what I know about my projectile, right? So I've taken my projectile, I've broken up into x and y components. Now I'm going to add in my monkey and then mash it all together, and hopefully magically it's going to make sense. So my monkey, what do I know about my monkey? Well, he's starting at some position, and this is 0, right? So I've made this 0 over here already. I can't reposition 0. So this is 0. So I'm going to say he starts at some height. I'm going to use capital H for this. So start at some height. He's going to drop to this point, right? So where his final position is the h that we're interested in. His initial velocity is going to be 0. His final velocity, I don't want to deal with it, so I don't know. And the acceleration is going to be negative g, and the time it takes for him to fall that far is going to be t. So the time all happens at the same time, right? So I fire it in the x, y dimensions, and the monkey drops at the same time for this to work. So notice what I have. So I have two legs here. So I have d and h. And this angle, we're saying if you shoot this angle, that's going to hit it. So let's think about this. What are we saying? So we're saying this angle, well, what do I have? Two legs of a triangle. So two legs of a right triangle. right? So if I draw my little triangle here, so this is D and H, so we can write this angle in terms of capital H. We can write this in terms of D and H, so I would say this is going to be, that's the tangent, so to get the angle, I'll take the arctangent, so this is going to be arctangent of opposite, so H over D. So, so this is what we're saying that it's going to come out to, right? So we're saying that for this, if we can mash all this and end up with something like this, this is telling us that, you know, the angle is only a function of the height and the distance. Okay, so let's see how we're going to go about this. Well, I'm thinking I'm going to make a few equations here. So let me make this one. So this is going to be velocity in horizontal direction. So I can say my velocity in my horizontal direction, which is v cosine theta, my original velocity, right? So this is going to be equal to distance over time. Yeah, I can rearrange this to say time is going to be distance over v cosine theta, right? So I'll hang on to that one. I'm sure that's going to be useful. So time is often a connector. So, and that, I don't actually remember how to do this, so hoping this works out. So let's see. So I'm going to start here. I don't want to deal with final velocity, so it only leaves me one equation to work with, and that's going to be this one, which says that my final y position, which is h, is going to be equal to my initial y position, which is 0, plus velocity times time, which in this case is v sine theta, so my initial velocity times time, plus 1/2 at squared, so I'm going to call this minus, because I got a g there, 1/2 gt squared. Okay, well, yeah, I don't want to be squaring stuff in here. That's going to get ugly, so let's see what else we can do. So this is a description, so notice this description for the vertical dimension. So let's deal with the monkey. So in my monkey, again, I don't want to deal with final velocity, so I'm going to use the same equation, which is going to say that my y position, my final y position, which is h, is going to be equal to my initial y position, which now is not 0, so now it's capital H. Yeah, capital H over, how do I get t here? Oh, this is, yeah. Okay, so capital H plus my initial velocity times time. My initial velocity is 0, so that's fine. And times, well, I'm going to add into this 1/2 at squared. Again, I'm going to have the same negative 1/2 a, which is g and t squared. Okay, well, let me think about this for a second. So what's this telling me? So time is going to be the same, right? So I want them to both fire and end at the same time point, but also I want them to be at the same place at the same time. So that means that this is going to be the same. So I've used lowercase h, and is it valid to, I could set these equal to each other if I wanted to. I don't think I will, but so this is valid. So this h means the same thing as this h, so they're ending at the same position. And time, this means same as this time. So everything else is correct. So what I'm going to do, so notice I've got this 1/2 gt squared that shows up here twice, and I don't want to deal with it. So what I'm going to do is I'm going to solve this one for negative 1/2 gt squared, right? So I could say, well, negative 1/2 gt squared is equal to what, I'm just going to move this over here, so it's h minus capital H. And I'm going to take this, and I'm going to place it into here for that. Right, so I'm just trying some things and hoping it's going to work out. So I'm going to plug in here and then try to simplify. So I'm going to take this equation down here, which is h is equal to v sine theta times time. And now the negative is going to go away. I'm going to be left with plus h minus h. So good. So what's disappearing? So notice what's happened. In this, I'm going to get rid of h, so I'll move this h to the other side. These two are going to go away, right? So the ending position isn't going to matter, and you kind of knew this already, right? So if I fire it more quickly, they'll still meet, but different height. If I fire it more slowly, they'll still meet, but at a different height, right? So the height they meet at doesn't matter. What's going to matter is really the angle. So let's see. So that h goes away, which is good. I didn't want to have it there in the end. So now I'm going to be left with, I can rearrange this and say h is going to be, my capital H is going to be equal to v sine theta times t. Well, I still have t, so that's kind of a hassle. But fortunately, I have my x position. So I'm going to take time. I'm going to plug in this into there to make this work. So I'm going to have h is going to be v sine theta. And I'm going to replace time with this, d over v cosine theta. And oh, look, I have velocity on top and velocity on bottom. That's going to cancel. So turns out velocity doesn't matter. That's good. I need to get rid of velocity. So I'm going to be left with h is equal to d times sine of theta divided by the cosine of theta. Sine over cosine, that's tangent. So I can say tangent of theta is going to be what, h over d? And then to get to theta, the angle that I need to send it to is going to be the arctangent of h over d. So notice what we've gotten to. So we've gotten back to what we were trying to prove in the first place. Right? So this is saying the only thing that matters is the angle, which is dependent upon how high this is and how far away you are, right? So if you make it taller, right, your angle is going to change. You're going to have to shoot someplace different. But what it doesn't depend on, right? So notice we got rid of velocity, so it turns out, right, we canceled velocity, so the velocity you shoot it at doesn't matter at all. And there's an interesting extension to that. So the velocity, you know, it doesn't matter at all, and the what else doesn't matter? So the position where they meet, you know, I don't know what it is, but they meet there. So that meeting spot. So how can velocity not matter at all? So think about this case. So what if I shoot it really slowly, right? So here's my monkey. He's going to drop, and I'm going to shoot it here, and it's just going to go like this. Right? How can this be valid, you say? Well, you are thinking too much about the ground. So imagine the ground's not there, right? So what's going to happen? This is going to keep going on this parabolic path, and the monkey's going to keep falling, and eventually they'll meet. And they may meet well below the level that it was fired, or so you could have a negative height that they meet at if you set this to 0. But as far as the physics is concerned, right, you don't have to fire it with hardly any velocity. So any single velocity that you use that's positive is going to result in the monkey being able to catch it. So notice you can't shoot it straight down, but any positive velocity is going to end up allowing the monkey to catch it as long as you're aiming directly at it. So anyway, fun algebra to play with. A few steps. Kind of happy that I got there in the end. So sometimes you just got to back up and try again. But again, if you list things out and you're careful about the things that are the same, it usually works out. Hope that helps. Bye.